Hello, everybody. All right. So in this video, we're going to talk about overview of a channel coding, in fact, of linear block coding. So let's start with first the overall block diagram. Okay. So first, let's say you have your data, and you're going to do channel coding first. Channel coding. Okay. And then you're going to transmit this through the binary symmetric channel with a transition probability p. For now, the p is not important. It will come into our calculations later. But it's a binary symmetric channel which will just flip bits randomly with a probability p. And then the output, when you get your bits, you're going to do channel decoding, and then hopefully you get back your data. Okay. All right. So now let's dig in a little bit deeper into what's going on here. So what is data? Data is your just random bits, which could be zeros and ones, which are random sequence of bits. Okay. So now we said we're going to do block coding. That means you're going to chop your data into blocks. Okay. And usually, let's say if you chop your data into, let's see, okay, chop data into blocks of length 4, then we denoted this with a symbol k. So in this case, k equal to 4, right? So let's say you have your sequence of data 0 1 0 0 1 0 1, something like that. Then you're gonna chop this up into, starting from here, 0 1 0 0, and then 0 1 0, and let's say this was 1 1, and then so on, right? So basically you're taking a stream of data bits and then dividing them into blocks, in this case of length 4. Okay, so each block is a message word, and we denoted this with m. Okay, so this is like m1, m2, m3, and so on. So we have sequence of blocks now instead of sequence of bits because we group them into blocks. Okay, so now that means that the input of the channel coding we have m, right? And at the output we get, c, which is you convert a block of data bits into block of code bits. Okay, and this block of code bits is called a code word. Okay, so let's look into the channel coding a little bit. So this is channel coding. Okay, so the input is data blocks or message words, and the output is code words. Okay, and then the length here we denoted with letter n. Okay, and then in the class, for example, we were talking about let's see, k equal to 4, and n equal to 7. Okay, that means we take a block of data which is 4 bits and produce a block of code words or code bits which is of length 7. And then k and n could be varying, depends on the specific block coding you're using. Okay, all right. So now then we talked about linear algebra, like how do you convert this into linear algebra? So first, what we do is in the linear block coding, when we have a message word m, right, you append that. So if let's say if m is, you represent m with a column vector, let's say 1 0 0 1, something like that. Okay, then c would also be a column vector with the first bits being the m itself, followed by the parity bits. Okay, now the p is the parity bits. All right. So then, okay. So how do you get these parity bits? We get the parity bits by multiplying m with the parity generating matrix p. Okay. So this is a parity generating matrix. Parity generating matrix. Okay. Okay. So this is how we get our parity bits, right? So to summarize, what happens to the transmitter is you start with a message word. Then you calculate parity bits as by multiplying the message word with the parity generating matrix. Okay, and then you form a code word C, which is the message word that means all the bits in the message word, followed by the parity bits, and which is given as M times capital P times M. Okay, so that's your code bits. Okay, and then you transmit your code bits through the binary symmetric channel, and then out comes C hat. Okay, so if you're lucky, C hat will be equal to C, right? But if there are errors, C hat will not be equal to C, and that's the problem. No, right. So then, so first of all, you need to, so the receiver, right? So first, check if C hat is valid. Okay. So when is C hat not valid? If the transmitter, if you know the transmitter cannot transmit C hat, it is not valid, right? That means any code word, which transmitter transmits is a valid code word, right? Is a valid code word, right? So it is possible that you receive something which you know the transmitter will not transmit. So for example, you know, if you receive something, right? So let's say C hat is equal to M, let's say M hat, and P hat, right? And P hat. So let's say if P hat is not equal to capital P times M hat, right? Then you know the transmitter did not transmit this exact code word, right? So what does this mean? This means there is at least one bit error. Okay, so now remember the contrary. Let's say if P hat turns out to be equal to capital P times M hat, that does not necessarily mean there is no error, right? But we'll get there later. But if it turns out that this is not equal to this, you immediately know that there is something wrong, right? Because if the transmitter, whatever transmitter transmits, it will make sure that the parity bits are obtained from the message bits using the matrix multiplication. If that rule is not satisfied, you know, then there is something wrong, right? So in other words, what you're saying is, here is if P hat not equal to capital P times M hat, there is an error, right? There is an error. Okay, so remember you're now in this new number system in Z2, right? So in Z2, this implies P hat plus capital P times M hat equal to 0. Okay, so if you want to convert this into matrix form, what you can say is, let's see, so P hat plus capital P times M hat, right? So you want to convert this into matrix form, you can say P and identity matrix times your M hat and P hat if this is equal to 0, right? So this is not equal to 0, there is an error. Okay, so now, oops, we can call this new matrix, which P and I is equal to syndrome S, which is a syndrome matrix. Okay, and the resulting value we can call a syndrome. So small s will be equal to capital S times C hat, and small s is syndrome. Okay, so that means now what we're saying is if s is not equal to 0, then there is an error. Okay, so now at the receiver we know how to detect if there is an error, right? Now the next question is, let's say you detected there is an error, then how do you correct it? That's the main thing, right? So remember, we are talking about we want to make single error correcting codes. Okay, so it means if there is a single error bit, you should be able to correct it. And that means you should be able to know, pinpoint exactly where that happened. So in order to do this, we have to look a little bit more carefully into what's happening with the channel, right? So the binary symmetric channel. Okay, so in comes C, out comes C hat. Now the binary symmetric channel is basically flipping bits randomly, right? So that means, you take your original code bits and plus you XOR it. That means in Z2 you're adding it with some error bits to get C hat, right? So for example, if C is, let's say 1001, and then I'll say 110. I mean, this may not be the exact parity bits depending on the situation, but I'm just taking it, for example here. So let's say if this is C, right? Then I want to flip this bit, flip the fourth bit. So I can take an error vector, which is 0, 0, 0, 1, 0, 0, 0. Okay. So if I say C hat is equal to C plus E, if you XOR this, that means whenever you XOR something with 0, you get the same thing, right? That means only the fourth bit will be flipped. So I'll get Y 1, 0, 0, 0, 1, 1, 0, right? Only the fourth bit flipped here. Okay, so bit flippings can now be seen as adding error. Okay, so now I have C hat is equal to C plus E. So the binary symmetric channel model will become like this, right? Where you have C, you're adding E, and then you're getting C hat. So now this is the binary symmetric channel, which is modeled by a simple addition of a random error vector. Okay. So now let's see what's happening from a more linear algebra perspective to when you add an error like this. Okay, so first of all, let's see. So at the transmitter, we know that my parity bits will be equal to let's see what capital P times M, right? So this means let's see. My parity bits plus capital P times M equal to 0, or in other words, my S times C equal to 0. Okay, if C is a valid code word, my syndrome matrix times C should be equal to 0. Okay, so now I receive a C hat. What happens? So at the receiver, whatever I receive, I'm first multiplying with S and seeing if that is 0 to detect an error, right? So let's say there is an error and C hat is equal to C plus E and E is not equal to 0. That means there is an error. So let's see what happens if I multiply S with C hat. So I get S times C plus E. So this would be equal to SC plus SE, right? So now we know that if C is a valid code word, SC should be equal to 0. Right? So then what we have is SC hat equal to S times E. All right. Okay. So now the real question is, if we want to figure out exactly what C was, we know C hat because that is the output of the channel. Okay. We don't know E, right? If you know E, then it's very easy to figure out what C is, right? So let's say if C hat equal to C plus E, right? And you know E, then it's very easy to get back C because C will be equal to C hat plus E, right? Okay, so you can see this, like I'm going to substitute C hat from here, it will be C plus E should be equal to C. So that means what this means is if you know exactly where the bits flip, that means you just go back and flip them back, right? But the problem is you don't know what E is in general. Okay, so in general, you don't know E. But if E has only one, right? That means if there's only one bit flipped, then you can figure out you can figure out E exactly. Okay, so how do we do that? Let's look at that. Let's see what happens. Let's say I'm going to represent S as this is a matrix S, and then we know this is, let's say, let's say number of this is a 3 cross 7 matrix, right? So that means there are 7 column vectors, right? We know the number of columns should be 7 because you're multiplying this with c hat, right, on the right hand side. So I'm going to represent this as S1, S2, S3, S4, S5, S6, S7. Okay, that's my S. So now let's see what happens if you do S times E. Okay, so we're gonna S1, S2, S3, S4, S5, S6, S7 times E1, E2, E3, E4, E5, E6, E7. Okay, so I can represent this as sigma I equal to 1 to 7 EI SI, right? So because I'm just multiplying this vector, basically I can treat this as if I can treat this as if these are just numbers, and I'm multiplying this vector this way. That's beauty of linear algebra, right? So even though these are vectors, the multiplication will be resulting as if you're doing this, right? And remember, in here, each SI is a vector. Okay, this is a linear combination of vectors now. Okay, so let's say, for example, only E4 equal to 1 and EI equal to 0 for all other I. So this means my S times E will be equal to S4, right, from the above summation over there. So what does this say? That means, let's say if I had, and we know that S times E should be equal to, let's go up here. We know S times C, where is that? We know S times C should be equal to S times C hat. Okay, because we saw S times C should be 0. So we know this, and we have C hat. So what this comes down to is, you have C hat, you calculate S times C hat, and this is a syndrome, and you match S with the columns of capital S. Okay, so if S matches with the fourth column of S, that means there is an error in the fourth bit, right? So that's how you figure out exactly what E is. If E has only one non-zero element, right? Otherwise, you see here, if there are more than one ones in the error vector, then the resulting summation would be sum of two different vectors, and it will be difficult to figure out exactly where they are, okay? So, but if there's only one column vector, you match with a specific column vector, and then you figure out exactly where the error is, right? Okay, so that's the process. Let me summarize that process here, right? So you have your M. Okay, in the channel coding, at the output you get C equal to, let's say this is channel coding. The output you get C equal to M and capital P times M. And then this is the binary symmetric channel, right? You're adding an error vector E and you get C hat. Okay, and then let's come like here. Okay, so this one here is the transmitter. Okay, and then this is the channel. Now at the receiver, okay, so output of the channel is C hat. Then the first thing you do is you calculate the syndrome, right? So you calculate S times C hat, and then you get S, right? So let me call this syndrome detector or syndrome calculator, whatever you want to call that. So S will be equal to capital S times C hat. Okay, so this is a linear operation. and then after this, match S with, let me match small s with columns of capital S. Okay, and then that will be where the error is. And then once you do that, you make the correction. Make the correction. Okay, so this is the whole decoding process. You first calculate the syndrome. You then once you know the syndrome, you match with a specific vector, specific column in S, and then you know where the error is, and you go make the correction. Okay, so that's pretty much it. The linear block coding. Okay, let's see. So now let's talk about Hamming codes. Okay, so in the lecture we said for any linear block code with single error correcting block code, it has to satisfy that 2 to the n minus k should be greater than or equal to n plus 1. Okay, so that means when at the lowest, when 2 to the n minus k is lowest, you'll have 2 to the n minus k will be equal to n plus 1. So now when this happens, these codes are called Hamming codes. Hamming codes. Okay, when this particular equation is satisfied, right? So note that in general, n minus k is the number of parity bits, right? N is the length of the code word, k is the length of the message word, 2 to the n minus k is the total possible. Okay, so let's talk about that later. So, but n minus k is the number of parity bits. So in general, for singular correcting codes, you need 2 to the n minus k should be greater than or equal to n plus 1. All right. So, and then we will talk about why this inequality has to be true from our syndrome matrix perspective. And when the lower bound is reached, when that means if 2 to the n minus k is equal to n plus 1, the codes which satisfy that are called Hamming codes. So first, let's talk about why this has to be true. 2 to the n minus k, why that has to be greater than or equal to n plus 1. All right. So let's see. So now let's see. Okay. So we said at the decoding, if you receive c hat, you first calculate s times c hat. Okay. And this is a syndrome. And then you match s with columns of capital S, right? And depending on which column which matches, you know that's where the error is. For example, if S matches with the fourth column of S, then there is an error in the fourth bit. Okay. Or if S matches with the fifth column, there's an error in the fifth bit, and so on. Okay. And that is assuming as C hat only has one error. Otherwise, this doesn't count. Okay. So let's see. What is the dimension of S, right? So now S is pi, and you're multiplying this with this capital P and identity. You're multiplying with c hat, which is m hat and p hat, right? So m hat is k cross 1, p hat is n minus k cross 1. So total, the length would be n minus k plus k would be n, right? So obviously c hat would be the same length as c, which is the code word. So now this means you get p times m hat plus I times p hat. Okay, that's what you have. And this is the parity generating matrix. Now parity generating matrix, if you see, so you're multiplying with m hat, right? So this means this has to be, the number of columns in P has to be k. Okay, and let's see. Now if I is being multiplied with p hat, then this I has to be n minus k cross n minus k, right? Because p hat is n minus k cross 1. That means the number of columns in I should be n minus k, and so should be the number of rows. Now, since you're stacking p and I side by side like this, you're concatenating I to p in the rows, in the row dimension. That means the number of rows in P should be equal to number of rows in I. So that means P has to be n minus k. This is also obvious because P is the parity generating matrix, right? So that means P times at the transmitter, P times M will be equal to P at the small p. That means the number of rows in P has to be equal to number of parity bits. Okay, so now S is n minus k cross n matrix. So that means, okay, all right, and then we know, and then we are saying that there is an error. There is an error in the ith bit if small s matches with the ith column of capital S. Okay, so that means the number of locations you can actually correct is equal to the number of columns in S, right? So this means number of locations you can correct is equal to number of columns in capital S, right? All right, so now if there are n bits in C hat, right, then the number of locations you can correct is also n, right? So n will be equal to number of locations you can correct. Okay, now that means if you want to correct n bits, right, or let's see, let me phrase it another way. If you want to correct 1 bit error in a code word of length n, then you need at least n columns, in capital S, right? So this is a very important point here. I would encourage you guys to pause the video and maybe go back a little bit if you need to, and make sure that you understand this point. This is a very key point here, right? So let me myself do a very slight recap here. What I'm saying here is, so let's go back all the way here, right? So let's see. All right, so the way you do this is you match small s with the columns of capital S. And whichever column that matches, you say that's where the error is, right? So that means if you want to correct single error bits in the code word of length n, that means you need at least n columns in S, right? Because you need at least that many columns to pinpoint the exact locations of errors. Okay. All right. So that means the number of columns in S should be at least n, right? So now, if S is n minus k cross n, number of rows in S is n minus k, right? So that means, let's say so now let's say n is equal to, for example, if n equal to 7 and k is equal to 4, then S is 3 cross 7. Okay, that means each column in S is a binary, let's say 0, 1, 0, for example. This is a 3-bit binary number. Okay, that means each column in S is a 3-bit binary number. That means n minus k bit binary number. So let me write that down. Each column in S is a n minus k bit binary number. Okay, and you need at least n columns. Okay, so let me, okay, so if each column in S is an n minus k bit binary number, right, and all columns in, now here's another important point, is the columns in S have to be unique, right? The columns in S have to be unique, otherwise when if there are two columns which are the same and your small s matches with one of them, then you don't know how to pinpoint between these two, right? So let's say if this is S and this column is the same as this column, let's say this is fourth column, and then you say, and this is sixth column, let's say, and then your small s matches with both of them, then you don't know where the error is, right? So it means all the columns in S have to be unique. Okay, so all the columns in S have to be unique, and there have to be at least n columns, right? And we know that each column is n minus k binary bit. So if you have n minus k binary bits, the maximum number of bits, binary bits you can make is 2 to the n minus k, is the total number of binary bits, binary or binary numbers. Okay, and you need at least n. So that means 2 to the n minus k has to be greater than or equal to n, right? Now notice another thing. Notice another point is none of the columns in S can be 0, right? Because when small s is 0, you're saying there is no error. So if it, and then we are also saying that if S matches with a particular column, then that's where the error is. So that means none of the column have to be 0, because if this S is 0, we're saying there's no error. That means it should not, 0 should not match with any of the columns. So that means we cannot count 0, right? So that means the number of columns should be n, and none of them should be 0. So that means in the 2 to the n minus k, one of them is a 0 vector, right? And we cannot count that. So that means we need at least n plus 1, right? So that's where that comes from. Okay, so when 2 to the n minus k is exactly equal to n plus 1, we know that those are Hamming codes. That means in the syndrome matrix, we're using up all 2 to the n minus k except 0. You're using up all 2 to the n minus k binary numbers, right? So okay, so that's okay. So for Hamming codes, you're using up all the 2 to the n minus k columns, and that's where the efficiency comes from, right? So let's go into the syndrome matrix again. Let's say the Hamming code. So now let's construct this Hamming code of 7, 4, right? That means n equal to 7, k equal to 4, n minus k equal to 3. That means we know syndrome should be 3 cross 7, and this should be equal to p and I, right? And we know this I should be equal to 3 cross 3, right? So that means this p should be 3 cross 4, right? So now we know what this 3 cross, let's see. So we know what 3 cross 3 identity is. That is 1, 0, 0, 0, 1, 0, 0, 0, 1, right? And of all the 7 possible, of all the 8 possible 3-bit binary numbers, there is 0, 0, 0, and you cannot use that here, right? So that's gone. And then we have 3 more here. So that means there are 4 left, and all the 4 will come here, right? So let's write down the other 4. So this 1, 0, 0, 1, 0, 1, 1, 1, 0, 0, 1, 1, and then 1, 1, 1. These are the all remaining 4, right? So these are the 4 plus 3, 7 plus 1, 8. So we're using up all of them, okay? So that means I can use this particular matrix here as my P, okay? So now that I know what P is, that means I know how to generate my parity bits. I'll use this matrix P to generate my parity bits. So let's say M is equal to, in general, it could be M0, M1, M2, M3, right? So let me, okay. So according to this matrix, my P is equal to 1, 1, 0, 1, 0, 1, 1, 1, and 1, 0, 1, 1. Okay, so it means, and I'll get, and P times M is equal to small p, and let's say small p is P0, P1, P2. So according to that, my P0 is equal to M0 plus M1 plus M3, and P1 is M1 plus M2 plus M3, and P2 is equal to M0 plus M2 plus M3, right? So previously we saw rectangular codes, and we know in the rectangular code we arranged all the message bits into a rectangle and figured out parity bits like that, right? So now we have a different sort of combination, right? So you have M0, M1, M2, M3, and then P0s are given like this. So if you want to arrange them, and if you want to show this coding visually, what we can say is, let's say M0, M1, M2, M3, right? And then what you're going to do is we can, so for P0, we have M0, M1, and M3, right? So let's draw a circle like that, and then put P0 here. So what we're going to saying is we're going to assign a specific bit to this parity bit such that the total number of ones in this circle should be even. Okay, so that means if you add all of them up, you should get 0, right? If P0 is equal to some of these guys, if you add P0 plus all of these guys, you should get 0, right? That's what that means. In the circle, if you add all of this up, you should get 0. That means there should be even number of ones in this circle. Okay. Now let's see what P1 is. M1 plus M2 plus M3, right? M1 plus M2 plus M3. So draw that and then put P1 there. Again, you're saying if all the number of ones in this circle should be even. And then P2 is M0, M2, M3, like that. And this is P2. Okay, again, the number of ones in this circle should be even, right? So this is definitely not a rectangular formation, right? But this is a different formation. This is the basically 7,4 Hamming code, right? In the rectangular formation, we are saying number of ones in each row should be equal to even, and the number of ones in each column should be even. Here we are saying number of ones in each of the circles should be even, right? So if you notice, we actually derived this Hamming code, right? We actually designed this Hamming code. We started with designing the syndrome matrix, right? We started with designing the syndrome matrix. We know in the syndrome matrix, we know this should be I, right? And the only 4 other columns left other than 0, and we put all of them there, and we know that should be P. Okay, so then we said, okay, so if that is P, then we know, then you can use that P to generate the parity bits, right? And then that's how we did that. So generator matrix now should be equal to I P, right? This I is 4 cross 4 now, and this P is 3 cross 4, and then you multiply this with M0, M1, M2, M3, right? And you get equal, this will be equal to C. Okay, so now you know exactly how to do Hamming codes, right? So the key here is just designing the parity matrix. So we started with first designing our parity generating matrix. Once we know the parity generating matrix, we know how to get, if you go down here, we know how to get code words from our message words, and we know how to calculate syndromes using this S here. And then once you get a syndrome, you match that with a specific column, and that's how you know exactly where the error is, right? And that's how you do the decoding. So now we're going to do an example for Hamming code. You start from a data message word, you convert that into a code word, and then you do decoding. Okay, let's do an example now for Hamming code. And we'll use the same parity generating matrix. Okay, so let's go. 1 1 0 1 0. Okay, so parity generating matrix is 1 0 1 1 0 1 1 1 and 1011. So this should be 1. Okay, 1101 and 1011. Okay, so this is the parity generating matrix. So and then we're doing an example for Hamming code. Hamming code, coding, and decoding. Okay, so now let's look at coding. Let's say m is equal to some random 4-bit number, say, our vector 1100, let's say, transpose with that. Okay, so then the parity bits will be equal to capital P times m, okay, which already produced from over there, 10. This should be 1101 0111 1011, okay, multiplied by m, which is 1100. Okay, so this should be, note that this should be equal to sum of the first two columns, right? So this will be equal to 0 1 1. This should be my parity vector, right? So my code vector would be mp, right, which would be equal to 1100 011. That's my code vector. Okay, so this is what we will transmit over the channel. So now let's say the third bit flips in the binary symmetric channel, right? So c hat will be equal to 111 0011, right? If nothing flipped, this third bit should have been 0, but because it flipped, it became 1. Okay, and this is what you receive. Okay, but the receiver doesn't know where the flip happened, right? So it only knows that this is what it received. And so the first 4 bits, it will say m hat. M hat is equal to 1110, and p hat is equal to 011. Okay, that's what it has. And the hat, basically it has c hat. So the first thing at the receiver decoding process, step 1, calculate syndrome. Step 2, match S with columns of capital S. Okay, so let's first calculate syndrome, right? Small s is equal to capital S times c hat, which should be equal to capital P times m hat plus p hat. Okay, so let's calculate this first, and we know this is p hat. Okay, so then capital P times m hat should be equal to, let me see what p was, 1101. Okay, this was p, and then times m hat 1110. Okay, so what do I get here? So this should be the sum of first 3 columns. So 0 0 0. Okay, so p times m hat is 0 0 0, right? So that means my syndrome should just be equal to p hat, and syndrome will be equal to 0 1 1. Okay, syndrome is 0 1 1. So that means the error bit should be whatever column of capital S this is, right? 0 1 1. So let's go to capital S. Right, so let me write down capital S here. Capital S is PI, right? Okay, so this should be equal to, let me write down P first. 1 1 0 1 0 1 1 1 1 0 1 1, followed by identity 1 0 0 0 1 0 0 0 1. Okay, so which column is 0 1 1? 0 1 1 is third column. Okay, so that means the error is in the third bit. Okay, so my C hat was, again, I'm going to copy from here, 1110011, right? One 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 zero zero one one. This is my C hat, and then I now know that the error is in third bit, or at least I think the error is in third bit. So I go there and flip. So my estimate of C, let's call tilde, is 1100011. Okay, so in this case, it turns out that there was only one error, and my C hat, C tilde, is actually equal to C. So I corrected the error, right? So this way you can see that if there's a single error there's only a single error in the transmission, then you can actually correct it using this method. Okay.